we considered one example of the system, and we understood that the various parameters related to the system, like excitation pole, system poles, and corresponding to each of the kinds of poles, we have corresponding outputs, steady state output, and the transient output, transient response. Okay, and the condition for stability, right, is a limit that output as t tends to infinity should be lesser than infinity, should be a finite value. So this is what is our first requirement, right, as we understood. Now let's take another case. Okay, so this is example number 2. So let us say that there is a system with the transfer function denoted by, say, T of S, which is output, C of S divided by the input R of S, given by, let us assume this is 10 divided by S minus 2 into S minus 4. Okay, I'll just make one of the changes, not both. So previous case, if you consider, it was 10 by S plus 2, S plus 4. One of them I changed to minus. All right. So, and let us assume the input as, so let the R of S is unit step function. So you know that it is 1 by S, right? Is the Laplace. So this implies, let's calculate the C of S is equal to the transfer function into R of S. Correct? Okay. So transfer function is 10 divided by this is S minus 2 S plus 4 into R of S is 1 by S. So in general, we can write this is 10 divided by S into S minus 2 to S plus 4. So that is C of S. So if you want to apply, if you want to find out the C of t, then I have to go for the partial fraction here, right? So we'll call this is equal to, say, A by S plus B divided by S minus 2 plus C divided by S plus 4. Okay, all right. Now, we will, okay, this is the C of S. Now, taking inverse Laplace, okay. Let's not find out ABC. That's not our issue as of now, okay. Taking inverse Laplace transform, I'll get C of t. So, what is the inverse of A by S? If it's A, okay. So, A, general, normally it is U of t, okay. A into U of t, unit step, plus the, what's the inverse of the second term, right? So this is B e to the 2t U of t plus C e to the minus 4t U of t. So I'll, in general, right, I can write it as, there is A plus B into e to the 2t plus C e to the minus 4t. So instead of U of t, I'll write t greater than 0. So U of t exists only on the right side of our right axis, right, y axis. So it means it is like this. So this is the answer. Now let us try to find out, right? Again, let's try to first let us try to find out the various parameters over here, right? What are the system poles? S minus 2, S plus 4. Corresponding to them, whatever S, the root you get, S equal to plus 2 and S equal to minus 4. Those are the roots. And there is one excitation pole, that is S equal to 0. Correct? 1 by S. In the sense, just equate the denominator to 0 to get the roots. Okay. First root, denominator S equal to 0. To find second root, you do S minus 2 equal to 0. That means S is equal to plus 2. Similarly, S plus 4 equal to 0. So S equal to minus 4. So these are the poles of the system, out of which 2 are the system poles. One pole, S equal to 0, is the excitation pole. So corresponding to them, right, we have, what is this? So the output that comes because of the system poles, what do you call it? Yeah, I'll show you. Right, you see here. So because of the system pole, you have a transient response, and because of the excitation pole, you get a steady state. Okay, so this is a steady state. This is the transient. Fine. So now I need to analyze what happens with the stability, right? So let's check this. I need to perform limit t tending to 0, the output, whatever is output, that is C of t, correct? So we don't have any problem with A, that is fine. A becomes A itself, plus B into e to the power 2t. What happens as the t goes to infinity? Are you sure? That, hmm, no, e to the infinity is not 0. See, if you have e to the minus infinity, that becomes 0. But right now, it's e to the power large number, right? Something, when you raise it by a large number, right, then that will be, right, equal to infinity. So a plus infinity plus third term will be 0 because you have a minus over there. Okay, negative powers. Fine. So this means this is equal to infinity, right? So this says, right, this is not stable, not a stable system. It should not be infinity basically, correct? Okay. So now what changed our stable system, which was like this? What was the change that we made so that system became unstable here? Did you identify that? Right. Uh, S minus 2, correct? S minus 2. Okay, so let's consider the first case, right? The first case, let's try to plot both both of them on the graph. Okay? So the first one we considered is like this, right? So this is the real of S, this is the imaginary of S. So for the first system, right, if you remember, right, systems of whole, right, we try to represent, we had S equal to minus 2 and S equal to minus 4, correct? Are the system poles. So S equal to minus 2, I assume maybe this is say 1, this is 2. 1, 2, 3, 4, right? So minus, this is 0, S equal to 0, minus 1, minus 2. So you denote the pole by X mark, right? So this is one pole, this is the other pole. So minus 1 and minus 2. So the first graph is the plot of our first example, all right? Uh, where you can see that the poles are located at so minus 2 and minus 4. Okay, so this is minus 2, this is minus 4. I'll update. So S equal to minus 2 and S equal to minus 4. Okay, so X marks indicate that location of pole, right? Similarly, if you consider the second case, one of the pole, right, we try to move it, we wrote it on the right side because that is S equal to plus 2 minus 4. So we'll write it that way. So this is 1, 2, 3, 4. 1, 2, 3, 4. Okay, so let me write the poles first. One is at S equal to plus 2 and one is S equal to minus 4. Right? So this is plus 2, this is minus 4. Right. So some idea we get here from this, right? That means if at all a pole is present on the right side of the y-axis. We call it as a S-plane, right? So this whole diagram is called as a S-plane. So here also we have the S-plane, right? On a S-plane, if you have a pole marked on the right side of the y-axis, right? Then that means the system is unstable. Because of this plus 2, right? You see that we got a e to the power plus 2t, correct? So as the t goes to infinity, this becomes infinity. So that's a major problem. So some idea we got now. Okay, what is the condition? What is the basic reason? A system that might tend to be unstable, right? Is that, yes, this is the answer. So you see here, everything is on the left hand side, right? So everything we see on the left hand side, so that this is a stable system. System is stable. But on the other side, we can see that anything that comes on the right is plane. If you see something on this side, that makes the system unstable. All right. So because of this -4, no issues. It's fine. It's not going to be infinity, right? But because of the presence of a pole on the right side of the S plane, we we understand that yes, system goes to be system becomes unstable. Okay. So what are the possible outputs that we might get, which takes the signal to infinity? We'll see them. Okay. So I'll write 1 point. Okay. As there is a pole on the right half of the S plane. This implies yes, correct. Ultimately, system is unstable, but I'm trying to write the reason behind that. The transient response, correct, that is e to the power 2t. The transient response corresponding to that pole, okay, tends to infinity. Tends to infinity as t tends to infinity. Correct? This, right? Therefore, hence the system is unstable. Right. So this means, right, as the time goes to infinity, right, there is an exponential term with the positive index. Transient will go, transient will keep on increasing the amplitude. So, right, so we'll draw such possible outputs could be something like this. Okay, so whenever the system is unstable, right, the possible output of unstable system, right, are as follows. We have two options, right? Let's look at. So this is the time versus maybe. Now we have a term C output. So what was the input? The input was unit step, right? So I'll just draw dotted line. This is the unit step input. So maybe I'm expecting an output to be equal to be reaching this one value as the time progresses, right? Something like this is what we expected, correct? That's a stable system, but now it is unstable, right? So you see your output will keep on increasing as the time progresses. Now you take the time till infinity. This is going to reach infinity because it's going to be exponentially increasing, correct? So I'll write like this to infinity. So, right, that's the value you get as the time progresses. This is unstable system. All right, and there is another possibility. We might get another shape of output. T versus C of T. Now, once again, let me consider this is the expected value of the output. But you see, there may be a term which is exponentially increasing that controls the bounds of your function. Okay, so maybe you have something like this. We'll see the exact example later. It starts, goes like this, comes down. You see, its amplitude is also increasing, correct, as the time progresses. And you see, it's increasing, right? So because of that, right now, what goes to infinity, these bounds will reach infinity. So that is also another possibility of this. So such unstable systems, if the input is removed, output may not come back to zero because it's already in a oscillating mode or increasing mode. It keeps on increasing, right? So output will tend to infinity, right? So uh, stability depends upon the location of the poles. All right. So ultimate thing to learn from the two examples which we have discussed so far is that, right, this is the important point. So therefore, the stability of a system depends upon, right? We said poles, but the technical term is called as the closed loop poles. Okay, closed loop poles. Now there's the question: what is a closed loop, right? So closed loop pole means it is a root of our characteristic equation. That's all right. Roots of characteristic equation. Right. So we understood. Now, if all the closed loop poles or the roots of the characteristic equation, you find them to be present on the left hand side of the S plane, we understand that that's corresponding to this explanation is corresponding to the previous case, right? So that is this term. You see here, if every root you find is present on the left side of the S plane, correct? S is equal to -2, S is equal to -4. So what happens corresponding to those poles, you get a transient response with the negative, right, powers of negative exponentials, right? So powers are negative, right? That means as the time goes to infinity, right, we get the transients decay, correct? Damped oscillations you can find out. Either the system, so generally we say that system will be damped, right? So such systems are going to be uh, the stable systems. Okay, let's write a sentence about that, saying that when the system becomes stable. So far we discussed about unstable system, right? Now we'll write about the stable system. Okay, so if the closed loop rules of a system lie on the left half of the S plane. So that means what? We have, right? So the answer corresponding to them very similar to this, right? Transient response corresponding to the poles will tend to zero as the time goes to infinity, correct? So this implies be transient tend to 0 as t goes to infinity, right? This is simply because of e to the power negative. Okay, anyway, I will not write that. As this goes to infinity, this means, right, system become stable. Right. So what are the possible outputs? We'll see them. Okay, so possible outputs of stable systems. Possible responses of stable system. One of the following will come. Okay, so that is this is the t versus c of t. So as we know now, we have the steady state output expected like this. So it's not going to come to the steady state immediately as soon as you turn on, but it's going to take some time, but it will ultimately reach that. Okay, so this is the one of the positive, right? Or I may get another response as well. I may get a what is called as a damped oscillation, right? So let's try to represent that in the form of it. This is the so I may have this as the expected. Okay. Now also I have an exponential function ready. Just like this. This is the damping of the bounds, right? Because of which you may have the graph. So as the time progresses, right, this damped oscillation will tend to 0 and you will reach your steady state at the end. Right. Now, we'll directly move on to, so these are the directly stable and unstable systems. Now we have another possibility of getting what is called as a, we discussed about another stability that is called as a marginally stable, correct? So let us look at the condition directly for the marginal stability. We'll not solve any example like that. Directly I'll give you the condition. Okay. So the next type of stability we discussed was marginally stable system. It was a marginally stable system or a critically stable system. Okay, so let's directly look at the condition. Critically, or it's marginally stable system. So let's directly look at the condition for them. Okay, so the condition is that I should, when I try to plot the poles and zeros of the system, I should get something like this, right? That is, so once again, this is the real and this is the imaginary, right? The fundamental condition is that you will have, now you see, this is the condition. Anything you get on the left side, right? It's stable, correct? And anything on the right side, it is unstable, right? Any pole is present, poles. We are not talking about zeros. No problem with the zero. You have a pole means you have a problem. Now you tell me where is the margin of these two cases? It's a margin. It's yeah. So if you want to look at the vertical displacement, then that will be the x-axis, real axis. But we are saying that this is my stable region, okay, and the right side is my unstable region, correct? So this y-axis, right, imaginary axis becomes the margin for that's where the things change as we move from left to right. So this correct. So the idea is that if you get holes on the y-axis, exactly present on the y-axis, right, then right, this is the condition. You should not have any poles on the right side, and you can have poles on the left side and poles on the y-axis. Poles on the y-axis is important, right? Whether you have a pole on the left side of the y-axis doesn't matter. You don't have, that's fine for us, right? That's the first condition. You can have you cannot have any poles on the right side. That's the second point. And you should have poles on the y-axis, okay? And they should not be repeated poles. You can have different poles. I cannot have the same pole repeated again and again on the same point. That's the very important condition, okay? Right. So for example, I'll write like this, say maybe this is j omega 1, this is j omega 2 minus j omega 1 minus j omega 2, like this. You see the omega values are not repeated, correct? It's not like at a same point called minus j2 I have two roots. No. Okay, so that cannot happen. So this is a case, right, in which we are going to get an output like this. I'll draw the even the possible output. This is time. This is c of t. Now, do you recall the example we gave for marginally stable system? What was the example? Yeah, please refer. Pendulum, right? You see, it's continuously oscillating. It's not, right. Its amplitude is not increasing, at the same time not decreasing at a given point, right? So constant oscillations, if you find, right, that is the example for marginally stable system. Now you see, its amplitude is not increasing, not decreasing. It's going at the same pace continuously, right? That is because of the system being marginally stable. Its output is not going to infinity, so you can call it as a stable, but it is not properly stable because it's not fixed. Output is not fixed. So that's what we need as a condition. So I'll try to mark the conditions here, right? The condition for critically stable or marginally stable is this, right? The first condition is that non repeated poles on the imaginary axis. This is the first condition. All right. So I should have non-repeated poles should be present on the imaginary axis. Non-repeated is very important. Should not repeat, right? Then whether you have poles on the left hand side or left hand side doesn't matter. Left hand side is corresponding to stable conditions, so they do not interfere in system becoming marginally stable, right? Whatever is present on the y-axis is important. So on y-axis you cannot have repeated poles. Okay, that's the first thing. And the right second condition is that I cannot have any pole on the right side. If you have any pole, it is unstable. So, right? So anyway, that's not that's obvious, right? So I will not write. So this condition is called as the marginally stable or critically stable. Now we have another condition. Now we highlighted that non-repeated. What happens if it is repeated? Okay, if it is repeated, the system become unstable once again. Okay, so if repeated poles on the imaginary axis, this means it is unstable. Okay, so let's look at an example. Oh, okay. So first we'll write a graph of the real and imaginary planes. This is real. This is imaginary. Okay, now you see I have repeated poles on y-axis. For example, I'll write 2 here, indicating that I have 2 poles at j omega, right? Corresponding to them, I should have 2 poles here at minus j omega. That means repeated poles do exist on the y-axis, right? So that means system is unstable. Let me try to write the graph corresponding to that. And if you try to plot the time versus the output, C of t, if we try to plot, this is how it's the unstable output. Okay, one of the unstable output will come. So in this case, you are going to get this shape. And so on. Okay, so this tends to infinity. Right. So then we have the case where we have a conditional stability that comes into picture. You put some condition on the parameter of a system, right? If that is not satisfied, the system will become unstable. If the condition, as far as the condition is satisfied, system is said to be the stable system. Okay, so that is our idea about the stability. Okay, so now right, so that's all about the fundamentals of the stability, right? And how to identify a system is stable or not by looking at the given equation of the system. All right, but you see, normally what happens is that, right, the system will be of a very what you call, system will have, system's characteristic equation will be, if it is s to the power 2, s to the power 3 or something, yes, you can solve by using a calculator to find out the poles, correct? So I can do that, like let's take an example, right? So this is the example. So identifying the position of the pole by simply solving an equation. Okay, so let's try to do that. So if at all I have, like, okay, let the characteristic equation of a system be something like this. It's the root of, it's the denominator of the given equation. Okay, the system's equation will be given. Let us assume that it's a denominator, that is s cubed plus s squared plus s plus 4 equals to 0. This is the characteristic equation. Now if I ask you that, okay, find out the position of the poles, what do? You will solve this. Yes, so please solve, use your calculator and solve and give me the, there are 3 roots, right? Because it is s cubed, right? So I need 3 roots now, s1 equal to, s2 equal to, and s3 equal. So the poles that we get are, first one is minus 1.74. So first pole is minus 1.74. No problem. Give the complete real and 0.371 plus 1.46. So other one will be 0.371 minus j 1.46. Now you try to identify the position of these poles, right? If I try to mark them, let me try to. They're not repeated, okay? One is plus something, one is minus, right? So this is minus, let me assume this is minus 1.74. Okay, that is S1. So where is S2? You see it is 0.371. You should move on the right side, then above. So this is one here and one, correct? So 0.371 plus J 1.4 will be the above one. So I'll call this is S2 and this is the S3. Now, what's your comment? Is it stable or not? It's unstable because two poles present on the right side of the S. So because of that, system is unstable. Yes. Now my point is that if you have up to s to the power 3, or maybe in some of the cases up to s to the power 4, if you have, you can solve directly by using calculator. Easily you can solve. Okay, but the practical case is that you don't get something like s2, s3, or like that. S to the power 3, s to the power 4 will not come in a practical scenario, practical situation. This term will be s to the power 6, s to the power 8, right? Then the problem is that we cannot keep solving 8 order equation. Solving takes a lot of time. Okay, so anyway, one option right now is to write a computer program, right? That's obvious, right? Nowadays you have several tools existing, right? But all such tools if you enter an equation, it will tell you that whether the system is stable or not by writing a program, works on a principle that is called as the RH criterion, Ruth Hurwitz criterion. So that's the important point, right? Which helps you in identifying, right, the stability of a system by just solving. You don't have to solve the whole equation. Okay, so let's try to uh, let me start. So right, this is one of the method used to find out the stability of a system, right, in a very easy fashion without solving the characteristic equation, right? Like if I have 8 s to the power 8, that means my solution has 8 different roots, right? The conventional method says solve for 8 roots, find out all the roots, check whether there is a root on the right side, then you give a comment saying that system is stable or not. That's the conventional method, which is very tedious. It's going to take a lot of time, right? So to overcome that, we have RH criteria. Okay, so in general, this is also called as the RH. Okay, so this basically works, right, by preparing by preparing a table. We have to form a table, and from that table, right, we will be able to identify whether the system is stable or not using a very simple inspection. Okay, let us assume that the characteristic equation B. Let's try to write it in this way. Okay, f of s is equal to, like, this is a naught into s to the power n plus, uh, okay, I'll write it this way. This is a1 s to the power n minus 1. So you see the power keeps on reducing. Like previous case, n was 3, right? S to the power 3. Next number is s to the power 2. Followed by you have keep reducing powers. Okay, the coefficient I'm writing as a1, a2, a3, etc. So a2 into s to the power n minus 2 plus, like that. Let's assume I have the last term possible is a constant an, right? This is my equation, characteristic equation. What you do normally, this is equal to 0 will be, right? So this is my function. Now, directly you form, so in order to solve the problem or to identify the stability, what we are supposed to do, we have to form the Ruth array, RH array. Okay, form the array. So the RH array is going to look like this. I'll show you the equation, and with respect to the equation, I'm right. Okay. So what we write here is the powers of S, highest power, start from highest power of the given problem. S to the n is there, then S to the n minus 1, S to the n minus 2, S to the n minus 3, and so on. We don't have to write all of them as of now. So we'll write all of them in the actual problem until the last power. So that is s to the power 0, right? You see here, this is an into s to the power 0, correct? So because I don't have a s, it's 1 for us. So it's just an, right? So that is the first column of our RH table. Okay, so I'll just separate them. Then next to that, I'm going to write like this. So all right. So you start with the coefficients of highest power that you write here. That is a to the a0, right? The next power will come below that. That is a1. Okay. But now you see you don't fill the a2 here. You will not fill the first column completely, right? Instead, you keep filling row wise for the first two. As a0, then a1. Next coefficient a2 comes here. A3 comes here. A4, A5, etc. Like that, you keep filling this. Okay, I'll write a few more terms so that I can show you the sum of the calculations required. Okay, so that for that purpose, I'll write few. So this is A6, A7, then both of them will continue like this, right? Like if your A not falls here, fill 0. Okay, so any term missing, you fill zeros over there. Let me assume that I don't have A6 term, but I need a A6, you put 0. Okay, like that. So you keep filling this. This is the first step. Then I need to calculate the values corresponding to next all the rows, right? Every row, whatever we have, right? We need to calculate the value dependent upon the previous two rows. In the sense, for the row number 3, that is this row, I have to use these two rows to get the value present over there. But what I do, I'll try to write, as of now, directly I'm not able to show you. I'll write some values. I'll show you the equation to be used. So say this is B1, right? This is B2, this is B3, etc. Right? We fill like this. And next row, I'm going to write it something like maybe this is a C1, this is C2, right? And so on. Okay, you will fill. So ultimately, you will get some value here. Okay, so like that, you keep filling. All right, now I'll show you an equation, the equations to be used. So let me show you how do I calculate B1. Right. So I'll write here. So the B1 is equal to, for calculation of any value, right, like such as B1, you will use, right, the first column values above that, first two column values, right, above that, and the column value that is corresponding to the next column of where you are finding B1. B1 means it is in the first column, so I should use A1, A2, A0, A3 divided by A1. Okay, so just look at this. I'll write the equation. It is A0 into A3 minus is it, oh sorry, A1, A2. It's upward direction first, then you subtract. Okay, so it's A1 into A2, A0 into A3 divided by A1. A1 in the sense from where you started, right? That term you divide. Okay, so that's how you calculate. So what should be this equation? A1, A2 minus A0, A3 divided by A1. That's for B1. If I want to calculate B2, this will be, you see, B2 is this, but you should use the first column for sure. You cannot change it. Okay, above that line, above the line which you are calculating, right? You have to use the first column for sure. But the second column will not be this now, it will be this. Okay, like that. So A4. Right. A1, perfect. So that is, I'll write once again. You can just see A1, A4 minus A0, A5 divided by A1. So can you tell me what should be for B3 now in that case? Hmm. A1, A6, perfect. A1, A6 minus A0, A0, A7 divided by A1. Perfect. Okay, that's how you calculate. Fine. Now let me, like this you proceed, right? How many coefficients you can calculate in the third row, B1, B2, B3, B4, like that you keep calculating. Somewhere it will become 0. Okay, so somewhere it will become 0, so you stop. You don't proceed after that because all of them will be 0 followed by. Right. Then you move to the next row. For example, C1 now. Right? How should you calculate C1? You should use this and this. Same rule. Rule still remains same. It's like so this should be B1, B1 A3 minus A1 B2 divided by B1. Give me the value for one more. I'll write C2. C2 should be, for calculation of C2, it should be B1 A5 minus A1 B3 B1 and so on. That's all, right? You will write the next row D1, D2, D3. You do the same, right? This is the fundamental equation you are supposed to use. That's all. Okay. You will apply this particular rule for any given whatever equation, characteristic equation, right? You apply that, you fill this first. Complete the RH table initially. Okay. Now, how do you identify? How do I identify whether the system is stable or not? Right? Is very simple. You don't have to find any solution. Right? Right? You don't have to solve the equation. I'll just give the condition here. If there is no sign change in the first column of RH table or RH array. If there is no sign change in the first column of the RH array, this implies the system is stable. So it's very simple, right? Just form a table and check whether there is a sign change in this. I just did this, right? In this particular column, right, we are talking about. So I should not have any sign change. What do you mean by sign change? Yeah, so I may have a positive term here. All, if the first term is positive, all the terms should be positive. That's what I'm expecting, right? If the first term is positive, first, second, third are positive, somewhere in the middle, I get a minus, right? Means, yes, there is a sign change. So the sign change indicates that there is, so actually the RH tells that if at all you have uh, two sign changes, two sign changes indicates that there are two poles on the right side. Number of sign changes equal to number of poles on the right side. That's the point. Okay, so that's how we try to identify, right? Whether, so ultimately there should not be a sign change indicating that no poles on the right side. That's all. Okay, so that's the explanation for the RH criterion, right? We'll start solving the problem from the next class.